The assignment that is due today is 3.2. 3.2 is on differentiability of our functions. So differentiability. Differentiability. Now, last time in class, I talked about 4 different points that are not differentiable. And so I do want to review that. Those are these are important concepts that we do need to remember. So at what points is a graph not differentiable? What does differentiable mean?
You can differentiate.
Yes. Differentiate, yeah, you can differentiate it. Well, what does differentiate mean? Okay, to take the derivative, yes. So the question is, where can we not take the derivative? At what points can we not take the derivative? Does anybody remember? There are 4 of them. What was one of them?
Where it's not continuous.
Yeah, not continuous. I heard 2 of them. So not continuous. A corner, a cusp, which is really sort of the same concept. Cusp, a vertical tangent, and a vertical tangent. Vertical tangent. Now, here's something, since we brought up not continuous, at points that are not continuous, well, now that opens up a whole new bag of worms, because we have 4 different points of discontinuity, or 4 different types of discontinuity. What are the types of discontinuity? Okay, we have oscillating. I'm going to spell it wrong. Is that awful? Did I spell it wrong?
I don't know.
It's either right or wrong. It's either right or wrong.
Oscillating. There we go. Oscillate. Double L. Oscillating. Is that right?
Yeah, it is.
Awesome. What's that? Okay. So oscillating discontinuity. What else?
Infinite.
Infinite.
Jump.
Jump. And removable. At all of these points, the graph does not have, it doesn't have a slope. It doesn't have a derivative. A cusp, so a corner looks like this, and a cusp looks like this. Y equals x. Y equals x to the power of 2/3 is an example of a cusp. Let's take a look. Are we good with zooming out? Anybody still copying? Okay. Let's go to Desmos. An example of a corner would be an absolute value. And I think it was, Kana, you said, is it always at x equals 0? And we talked about that last time. We're going to talk about it again, because I think that is sometimes, for a simplification, it might seem like the point that is not differentiable is always at x equals 0, and that's not the case. So this is a corner, right? This is, let's see, x to the power of 2/3. What kind is this? A cusp, because of these curves. So at this point right here, why is this point, can you put into words why this point does not have a slope? Yeah, when we converge to x equals 0 from both sides, we're getting different slopes. One is positive and one's negative. Which direction would give me a negative slope? If I come from the left-hand side, I have a negative slope. And then from the right-hand side, I have a positive slope. At that single point, I can't have two different slopes, so it's not differentiable at that point. And we can also do it algebraically to show that it's not differentiable at that point. How can I show that this algebraically, that this is not differentiable at this point at x equals 0? Well, let's differentiate it. What do we get? Power rule.
You get 2/3 times x to the negative 1/3.
And so we have a negative exponent. And so we just move that to the denominator using our negative exponent rule. So I have y prime equals 2/3 times, I guess we could even do the cubed root of x, right? Is that the same? Is that the same or not?
Yeah.
Okay, that's the same. And so what value for x would not be allowed?
0.
Yeah, x can't be 0. So that makes even sense, algebraically, it makes sense that the graph is not differentiable when x is 0. Differentiable is the slope. Does it have a slope? Does x equals 0 for this graph, for a cusp, do I have a slope right here?
No.
Why don't I have a slope?
Because it's not differentiable.
Yes.
You don't have a slope because it's two different slopes on the left side and the right side.
If I converge on that point from one side to the other side, I'm getting two different slopes, which doesn't make sense. Yes, Natalie. A vertical tangent, let's do a vertical tangent. I think one of the examples I used last time was y, actually this one works, y equals the cubed root. I think I have to go here for cubed root. I don't have the hotkey for this. The cubed root of x. We have a vertical tangent right here. What does a tangent mean? Yep, it's a line through 2 points that are on the graph that are infinitely close to each other. If you see, if I have one point here that's getting closer and closer to another point here that's getting closer and closer, then at this particular point right here, that tangent line is going to be what? That tangent line is going to be what? It's going to be vertical. Well, a vertical, what kind of slope is vertical?
Non-existent.
It's not existent. Isn't it 0? No, it can't be 0.
It can't be 0 because it is.
If I draw it,
0 on the bottom, but not on the top.
yeah, if I have a slope,
We just don't talk about it.
if I have a horizontal slope and I put a ball on a horizontal, sorry, if I have a 0 slope and I put a ball on a 0 slope, what direction does the ball roll?
It doesn't.
It doesn't, because there's no slope. Now, can we also say then that this has a 0 slope?
No.
No, that's not.
You can ball on a wall.
Yes, you can't.
You can't.
There's, yeah. I mean, you could say the slope is infinite, right? But yeah, we just say that this is undefined. Just say it's undefined. So why is a vertical tangent, why is a vertical tangent not considered a slope? Because it's undefined. Yep, it is undefined. So my rise is what? Rise of, I don't know, 10 and a run of 0. So that's a 0 in the denominator. Yep, which is undefined. All right, we good with that?
Yes.
Can we move on? All right. Here's a question that I want you to consider. Here's something I want you to consider. I don't want, some of you are going to look at it and you already know the answer, but I want you to hold your tongue. I want everybody to think about this question. Question mark. Don't say it. Don't say the answer. Can a function be continuous but not differentiable? I want you to think about it. Logan, what do you think? You think maybe? Do you have any examples? All right, fair enough, fair enough. How about Blake? What do you think, Blake? Can a function be continuous but not differentiable?
Yes,
Do you have an example?
not really. I'm just thinking of like the discontinuities.
Uh-huh. So all those, so there's 4 different types of discontinuity, right? What are they?
The removable.
Removable,
Jump.
jump,
Oscillating.
oscillating,
Infinite.
infinite. Which one am I talking about in this question? None of them. Why? Because this is continuous. Is a function, can a function be continuous but not differentiable? Winnie, what do you think? Can a function be continuous but not differentiable? What's that? A piecewise. So if I did a piecewise, it might be continuous but not differentiable. Okay. Gabby,
I don't know.
you have no idea?
No idea.
Natalie, you say yes? Do you have any examples? Nice. We talked about those. We have corners. A corner, or in fact, a corner, a cusp, or a vertical tangent. All of those are continuous, right? And they're not differentiable. So the answer is yes. Can a function be continuous but not differentiable? Yeah. Yes. What are my examples?
Corner, continue, or corner, vertical tangent, and cusp.
Any guesses what my next question is going to be?
Differentiable but not continuous.
Yeah, that's my next question. Thomas, good job. Can a function, don't answer. Don't answer. Let me write it down. I want you to think about it. I want everybody in the class to think about this. Can a function be differentiable but not continuous? Okay, think about it. Can a function be differentiable but not continuous? Ian, what do you think? Can a function be differentiable but not continuous?
Yes.
Yes. Do you have an example? Tate, what do you think?
I think no, because differentiable means that it's able to be.
That there's a slope.
So
So when, so not continuous, right? Not continuous. There are 4 different types of discontinuity. Tate, do you remember what they are?
there's removable,
Okay, removable looks something like this. That's messy. Let me try that again. A removable looks something like this. Okay.
jump,
A jump looks something like this.
infinite,
Infinite looks something something like this and oscillating. So the question is, do I have a slope here? Where I have a vertical asymptote? No, I don't have a slope there. What about over here where I have a removable? No, there's no slope there. There's no point. How does a point have a slope? What about here? Does this have a slope? No, because if I converge on both ends, but from either side, I'm going to be converging on a different slope. What about this mess over here? Can we tell what the slope is in here? No, I don't know what my rise over run is anymore. I don't even see the line. So we say, so then the question, Tate, is, can a function be differentiable but not continuous? And Tate, one more time, what's the answer?
No.
No, it can't be. In fact, so the answer for this one is no. And we talked about that before. Over here, we said points that are not differentiable are the following: if it's not continuous, or if the point is a corner or a cusp or a vertical tangent. So because all points that are not continuous cannot be differentiable, then we know that the answer for this has to be no. Does anybody have any questions about that? Jake, how do you feel? Jack, how do you feel? You feel good? Okay. All right. So let's move on. So what that means then is that differentiable implies continuous. What that means is differentiable implies continuous. The graph has to be continuous in order to be differentiable. All right, I want to talk about let's go ahead and do some, unless somebody has any questions about what we've talked about so far, I want to move on and talk about the derivative function. Okay, we good? All right, so what if I have, so find the derivative, or find dy dx of y equals 3x squared plus 4x minus 7. Well, now you can't see everything. Let me zoom out. What am I asking you to find? Yeah, this is one of our notations, dy dx. It's not dy over dx, it's just dy dx. dy dx is one of our notations for a derivative. So what is the derivative of this? What's the derivative? Madeline, what's the derivative? Oh, I'm looking at the wrong rule. Gaia, what is the derivative? Remember the power rule? So if I have y equals a times x to the power of n, what is my derivative? A times n times x to the power of n minus 1. Well, why even have the shortcut? Because without the shortcut, the only way to do this problem here, to find the derivative of this without this, yeah, I have to do this whole limit as h approaches 0 of this 3x plus h squared plus 4 times x plus h minus 7 minus this 3x squared plus 4x minus 7 all over h. And then I have to expand this and distribute this and distribute this and then combine like terms and then factor out an h so that the h's will go away and then plug in the 0. Or we can memorize this shortcut. Where did the shortcut come from?
Lots of people noticing patterns.
Lots of people noticing patterns. Thomas.
See, I actually did my own research on that, and according to Wikipedia and a few people who asked the question a while ago, in my third week, Isaac Newton and that German guy independently discovered the power rule.
Oh, they did?
Yeah.
Awesome.
They
Okay,
did have the power rule.
you were right. They did have the power rule. And I didn't know that. That's cool. Thanks for doing the research. Natalie. What's that? Yeah, we do the power rule for each of the terms individually. So Gaia, do you see the mess that we have to deal with if we don't memorize the power rule? Okay, so I want to memorize the power rule. And Thomas says that Leibniz and Isaac Newton both have discovered the power rule. They noticed the pattern themselves, it sounds like. So if I do this, Gaia, if I do this individually, then what is this? What's A? What is A? 3. What is N? 2. So if I'm using the power rule, I need to multiply A with the N, right? So if I multiply the A with the N, what do I get? 6. I have 6. 6x to the power of what? What do we do with the exponents? Yeah, we subtract 1 from the exponent, so that would be 2 minus 1, which is just 1. I could write it there or just ignore it. And then Gaia, what about this one here? 4x, what's the derivative of 4x? Okay, there's 2 ways you can really think, there's probably other ways, but if I think of this as an individual function here, doesn't this follow our mx plus b? Well, the derivative is the slope. So what's my slope? The slope is just 4. The slope for this is just 4. That's my m value. It's just 4. Now, the other way I could do it is I could still use the power rule. I could rewrite this as 4x to the power of 1. So if I use the rule, what are my a and n values?
4
Uh-huh.
and then
N is 1.
Yeah.
Okay, so we multiply both of those, right? To get what? All right, so I get 4. And then what do I do with my exponent? So I have 1 minus 1, which is 0. What's x to the power of 0? It's just 1. So I'm left with 4 times 1, which is 4. So I get the same answer. My slope or my derivative function for 4x is just 4. So we have a law, one of our laws of exponents says, let's look at 5 squared over 5 squared. Now 5 squared over 5 squared is 25 over 25, so that has to be what? It's 1. Now we also have a law that says if I have a to the power b over a to the power c, how do I combine this mess here? Yeah, a to the power of b minus c. Let's do that here. So that gives me 5 to the power of 2 minus 2, which is 5 to the power of 0. So 5 to the power of 0 has to be 1. Otherwise, there's something wrong with my laws. Let's check this one. Let's see if this actually works. If I have 5 to the power of 2, let's do this one. 5 to the power of 4 over 5 to the power of 2. I always hate when let's try something else. 5 to the power of 6. 5 to the power of 6 over 5 to the power of 2. Now, if I expand this, then I have 5 times 5 times 5 times 5 times 5 times 5 over 5 times 5. What can I do at this point? Yeah, I can start canceling some of these values. And so I'm left with 5 to the power of 4. If I use the same law that we had up here, would I still get 5 to the power of 4? Yeah, so it works. We know that these laws work. And they work because mathematicians saw patterns. All right, so if this works and this works, then anything to the power of 0 has to be what? 1. So what is x to the power of 0, assuming x is not 0?
1.
It has to be 1. Did I answer your question? Okay, cool. All right, so let's go ahead. What I really want to do, this is a really important part of today's class, is I want to come up. Yes. Yeah, let's do the derivative of the -7. Let's do, so I have -7 times x to the power of what? What is this x to the power of what for the 7? 0, yeah, because then it's just 1 and I'm left with -7. All right, so let's use our power rule, and the power rule says to do what? What's my a value? -7. What's my n value?
0.
So I have -7 times 0 times x to the power of, we need to subtract 1 from our exponent, so that's 0 minus 1, which is -1. But because this is multiplying by 0, then it's just 0. Let's look at this individually. What is y equals -7? Isn't that a graph that looks like 1, 2, 3, 4, 5, 6, 7? It's a graph that looks something like this. What's my slope? Yeah, 0. My slope is 0. A horizontal line has a slope of 0. So this piece here, Natalie, this piece here just disappears. Which makes sense, because what does this mean as far as a transformation? Doesn't that -7 as a transformation, all that means is the graph gets shifted down 7 units? So none of the slopes change. The graph just gets shifted down. So that makes sense why we ignore that piece there. It's just a shift down. The slopes don't change. All right, so this is what I want to do. I'm going to look at a graph like, let's look at a graph like y equals x, how about x squared minus 3x plus 4. Let's minus 4. No, minus 1. And I want to draw the derivative function for this. Now we could actually do this ourselves algebraically. In fact, let's do that first. Let's do this algebraically. I'm going to drop this in here. So we can find the derivative algebraically, right? What is the derivative algebraically?
2x minus 3.
2x minus 3. Do you agree with that using the power rule? My derivative function is 2x minus 3? Yes? Okay. What is a derivative function? What does that tell me? What's the point of a derivative function, Kyler? At any value for x. Yep. It gives me the slope of a tangent line for any value of x. Right, so we can do this algebraically. Can we do this graphically? Now let's look at this graph here. This is actually something that you will be responsible for on the AP test. Now, if this is my equation, and I want to find the derivative function for this. I want to find the graph of the derivative function. Well, where would I start? One good place to start is when we have a slope of 0. Where do we have a slope of 0 approximately? Yeah, that minimum we have do you guys see that we have a slope of 0 right there? So for my derivative function, I'm going to say, so this, for my derivative function, this is my x-axis. My y-axis is the slope. The y-axis is the slope. So my slope at this point right here is 0. From the right-hand side of this point, do I have a positive or negative slope? Positive. And on the other side? So the slope does exist. It's 0. In fact, let's draw our tangent line. Let's use green. Let's draw our tangent line right here. And a tangent line is defined by a line that goes to the graph at 2 points that are infinitely close to each other. So this is my tangent line right here. Why does this tangent line have a slope of 0? Because it's flat. Yeah, it's horizontal. Because it's horizontal. If I put a marble on that tangent line, it's not going to roll in any direction. So do we agree that for that, that we have a 0 slope at this particular point right there? Okay. Now, do we also agree that to the right of this x value, the original function has a positive slope? So we have something, I don't know, like this, that represents all of the infinite slopes that go from here. Looks like it, in fact, you can see it. Doesn't the slope get steeper and steeper and steeper? So that's going to be indicated with this slow progression upward. So we see that at first the slope starts to gradually get steeper, and then it gets really steep over here. So we get if the y-axis is now my slope, the slope is getting larger and larger as I continue on. What about on the left-hand side of where my slope is 0? Do you see that it's a little bit negative, but then it gets more and more negative as I go further to the left? So the other half of my derivative function is going to look something like this. Does it surprise you that the derivative function is going to be a line? If we have a quadratic, the derivative function graph is going to be a line. Yeah, look at the power rule. What does the power rule do? What do you do with the exponent with the power rule? You subtract 1. If I subtract 1 from a quadratic exponent, that gives me a linear function. So it should give me a linear function. And let's see how close we came to what we thought it would be. What did we say it was going to be? 2x minus 3. 2x minus 3. So we have a slope of what if we have a 2x minus 3? 2. So it looks like it should have been steeper, right? Yeah. It looks like let's go back. So it should have been something more like this, but you're not going to be graded on the steepness. You're going to be graded on your understanding, one, that the derivative function of a quadratic should be a line. And two, that you are correctly identifying the 0 slope and then whether you have a positive slope or a negative slope on either side of that. Those are the important things that you're looking at. If I wasn't given this equation here, I wouldn't know exactly how steep it is. Okay. Any guesses if I have my function is cubic? Yeah, a quadratic should be the derivative. So I have x, let's do x cubed plus 4x. Let's do minus 4x. Minus 4x. Yeah, that one looks interesting. So we're going to do this one here. We're doing the same thing. What are we doing? Can somebody describe what we're doing right now? More specifically, what are we doing?
Math.
What do I want you to, what am I trying to teach you?
Graphing the tangent and the derivative.
Graphing the derivative function. I'm trying to teach you how to graph the derivative function. Because on your AP test, they're not going to give you this other piece. They're not going to give you the equation. So I'm sort of cheating right now by giving you this. So in fact, let's not look at it right now. Let's not look at it right now. So if this was an AP test and you had to, can everybody see this okay? And I have to graph the derivative function. Where do I start? Yeah, where do I have a slope of 0? Yeah, we have one approximately here. Oops, let's use the right pen. We have one approximately here, and we have one approximately here. Okay, now what? What's the next step for graphing the derivative function? Is it Gabrielle? Okay, Gabby, yes. So what do I do from here? After I found my zero slopes, now what? Yeah, let's look at the slope in between these two 0 slopes. Is it positive? Is it a positive slope or a negative slope?
Negative.
Yeah, we see that as we read it from left to right, the graph goes down, it's negative. So that means it's all negative. Everything's negative between these two 0 slopes, right? Now, if the y-axis is my slope, here's another question. From here to here, can you describe the steepness of the slope when we go from left to right?
Well, it increases at first, and
It seems like it is, yeah, it's at first it's negative, but not very steep, right?
yeah.
I think it's this one.
way steeper.
And then it gets steeper and steeper, actually to what is called an inflection point.
Yes.
The inflection point is where that concavity changes, where we're going from concave up to concave down. That's actually an important word to remember in this class. Inflection point. Inflection point. An inflection point is where the graph changes its concavity. We don't use the word convex in this class. We only use the word concave. What does concave mean? Think of it as a cave. Here's my little cave right here. The cave part is the direction of the concavity. Is this part of the graph concave up or concave down? The cave part is pointing downward. We say it's concave down. What is the concavity over here? The cave part is pointing up. So we have concave up and concave down. What is the definition of an inflection point? The change of concavity. It is, inflection point is the change of concavity of the graph. And it's approximately here. Is that a good guess?
Yeah.
About here? Okay. So do you see that the steepness changes too at that point? Do you see at first the steepness is really gradual and then it gets steeper and steeper and steeper? Where does it start changing and being less steep? At the inflection point, yes. So I'm going to draw my graph to look like up until the inflection point, I'm going to get, if the y-axis represents my steepness, then I'm going to get steeper and steeper and steeper. And then at that point, with the inflection point, we get less and less steep. Is the slope right here positive or negative? You're look,
Yeah, because below those.
it's, yeah, remember the blue graph represents slope. And we have a negative slope. So this is going to be, maybe I should have been more specific with my question. For the red graph, is the slope is always positive from here to here. I actually forgot what my question was. All right, let's just move on. What about after this minimum point right here? What happens to the slope after this point?
It gets increasingly positive and steeper.
Yeah, it becomes increasingly positive and steeper. If the blue graph, if the y-axis for the blue graph is the slope, then to represent the red graph, it all needs to be above the x-axis. Agreed? So I'm going to get something like this. What about on the other side of this zero slope?
Positive.
Yeah, I see that the slope is positive. We read a graph from left to right, the graph goes up, so that's a positive slope. And describe the steepness of this positive slope as I continue closer and closer to this maximum.
Actually, closer and closer to the maximum. The slope slowly decreases.
Yeah.
Slowly, it's less intense, less steep.
It gets less and gets so. So over here, we have it. In fact, it's so steep over here, we're approaching infinity until we get closer and closer to here. Our slope is getting closer and closer to zero. So this piece of the graph should look something like this, which is the blue graph is a what? A quadratic. Let's graph this and see how close we came. So this is the one that we graphed. What was, now that we have the equation, what is the derivative of this?
3x minus 4.
3x
Squared.
squared minus 4. So I guess the question then is, I guess I'll do this. Copy it, paste, grab a piece, undo, paste it back in. How did we do? Yeah, you're not going to be measured on how far, because you're not given the equation, you're just given the graph. They're really looking for what? What are the important pieces that the examiner is looking for your AP test?
The inflection point and the direction.
You should know where the inflection point is. The inflection point is where we reverse our steepness,
0.
our zero slopes. That's what's important too. Those are really the important things that they're going to be looking for. Okay. Yes. Yeah. This was actually the last thing I really wanted to talk about. So let's look at something. What if I have y equals x 4 minus 3x cubed plus minus plus 2x. Ooh, that one looks sort of fun. Let's do that one. What kind of function family does this belong to? Quartic, yeah. The degree is 4, so this is quartic. What do you think the derivative function is going to look like?
Cubic.
It's cubic, yeah, because we always subtract using the power rule. We subtract 1 from our exponent. So let's go ahead and drop this in here. Zoom in maybe. You want some think time? So all of these, with all of these, I'm giving you the function and I want you to find the derivative function for it graphically. So you're finding all of the infinite slopes that this function represents. I think there's a software program. If you type in, find the derivative graph interactive, then there's some that where you draw it yourself and then it tells you whether you're correct or not. Kyler, are you stuck? So Kyler, what's the goal? What are we trying to do? Yeah, let's find our zero slopes. I think that's let's worry about the inflections later. Let's find our zero slopes first. That's I would argue that that's the best guidance you can start with is the zero slopes. Where do I have a zero slope? Approximately where? Yeah, almost 2. I see that we have one about right here. Okay. Where else do I have a zero slope? Okay, about 1. Yeah, I agree with you. Okay. Yeah, about -1. Where's that's my other one. All right. So we have 3 zero slopes. In fact, I think later on we talk about this, but I'm going to define it for you anyway. There's something called a local maximum, and there's something called a global maximum. A global maximum is the maximum, the largest maximum for the whole entire graph. This does not have a global maximum because this graph continues on up forever and ever. So we have what is called a local maximum. Do we have a global minimum?
No.
Yeah,
Yeah, we do right here. Is this a global minimum?
no.
No, because the global minimum is here. So what do we call this? A local minimum. That's a local minimum. All right, so we've defined all of our maxes and mins here. And then let's look at in between these two zero slopes here. Just looking at the slope between these zero slopes, looking at the red graph, looking at the slope, how can we describe that? It's all positive, right? Which means that for the blue graph, the y-axis is what? The slope. So is that going to be then between these two zero slopes? Is that going to be a graph that's below the x-axis or above the x-axis?
Above.
Above, yeah, because they're all of the slopes here are positive here. So we're going to say then that all of this is positive. We're going to go like that. In fact, if you look at it, let's describe it. Do you see that the slope gets steeper and steeper up until what? What's this called right here? An inflection point. How is an inflection point defined graphically? It's defined how?
Where the graph changes its concavity.
Yeah, what kind of concavity do we have here? Concave up. What about here?
Concave down.
Where does it change concavity?
That'd be an inflection point.
So yeah, at the inflection point. So that's where we start going, we get steeper and steeper and steeper to our inflection point, and then we get less steep, but it's all positive. It should all be above the x-axis. What about the slope on the left-hand side of this zero slope? It's very negative, right? In fact, it's super negative and it gets less and less and less negative to this point right here, right? So would it be okay if I just described it like this?
Yeah. Should be.
Yeah,
It's a different arrow. So you can equal minus.
it just keeps on going down like that. Yeah, it just gets steeper and steeper and steeper. All right, what is happening? Describe the graph between these two what do they call it? Extrema. Extrema would be your max or your min.
Negative.
Yeah, we can see that between these two extrema, we can see that the graph is negative. Can you describe the steepness between these two zero slopes?
Is it super steep and then
So we start here. What happens from here as far as the steepness?
It slowly increases in steepness.
Do you see it slowly increases its steepness and gets steeper and steeper?
Yes.
And then we get to a point, some point, which is called what?
The inflection point.
The inflection point, and then the steepness gets what? Less and less steep. Do you see that, Kina?
Yeah.
So for our graph, we're going to do something, I don't know, something like this, maybe. What does this represent? What does the green graph represent right there?
Slope of the red graph.
The slope of the red graph, and it's indicating, what does it say to us? What is this saying to us right here about the red graph? Because it's all below the x-axis. That the red graph is negative, has a negative slope there. Okay, what happens afterward, after this zero slope right here?
So it becomes about 30.
Yeah, it just gets steeper and steeper. Does that look like a cubic graph?
Definitely.
Yeah. Yeah. So there we go. Which should make sense. All right, let's see how we did. I'm going to, what should our derivative function be using our power rule?
4x cubed.
4x cubed
minus
minus 9x squared
plus 2.
plus 2. Let's see how we did. Let's do. So y equals 4x cubed minus 9x squared plus 2. And I'm just going to cut this and paste it in here so that we can compare how we did. It's not perfect, but what they're looking for when they grade your AP test, what are they looking for again?
The inflection
points,
point
zeros.
and
Compacted.
Yeah, okay, so they're looking for your zero slopes and the inflection point. Those are the big things that they're looking for. Another one? Don't we still have like 12 more minutes or something like that? 9 more minutes, okay. It feels like everybody gets restless and when we, all right. But then as a teacher, as your AP teacher, I get nervous. It's like, oh, we have to learn this. We have to learn this. And then in your mind, you're thinking, I have to have lunch. I have to have lunch. Yeah. All right. Okay. Let's look at, what if I have a graph? I'm going to just draw one. What if I have a graph that looks, oops. Here's a, for those students who want to practice this, my suggestion, well, is do what we did. What if you just make up some functions, try to get a lot of curves in there. You figure out what the derivative function graph should look like, and then you find it using the power rule to see if you're close, right? You could just do this on your own. You don't need me to give you guidance on that.
for the quiz, will there be an equation with it or will it not?
I don't think I really want you to practice figuring out the graph without the equation. Because that's how the AP test is going to be. They're going to give you a problem that's a graph. That would be the free response. They'll give you a graph and they'll ask you to draw the derivative graph for it. Okay, so let's say that we have something like, let's use a different color. Like this. And I want to, the directions are to find the derivative of the derivative graph for this. We'll call this my f of x. Oops. So where do we start?
Zero.
Yeah, we'll find out where our slopes are 0. Where do we have slopes that are 0? What's that? What's the slope right here? Louder? It's undefined. Why is it undefined? Because it's a corner. So instead, I'm going to just draw a little circle here. When I draw my derivative function, there is no derivative right there. All right. What is happening on the left-hand side of that no derivative?
It's positive, but the slope doesn't become steeper or less steep, so it's a straight line.
Yeah, this just turns out to be a straight line. Thomas, explain again why this is a horizontal line.
Because the steepness does not change whatsoever.
The steepness does not change whatsoever.
Slope is stays constant.
Correct. So this should be a straight line. Is everybody good with that? Okay. There's something else that happens here. What is it?
There's another
It's another corner, which means what?
no derivative,
There's no derivative.
no slope,
So I'm gonna just, I don't know, just do a circle here or something like that.
it'd be negative.
Okay. What's happening in between these two non-existent slopes?
Negative.
It's negative.
Yeah, that empty dot that's below the x-axis.
My goodness.
Now, is it gradually, should I connect these like this?
No.
No.
Piecewise.
No.
Do you agree that this should be a horizontal line as well?
Yes.
Why is it a horizontal line?
It's not changing.
Because the slope is not changing. And it's negative, which means what?
Below the x-axis.
It has to be below the x-axis, maybe down here. What's that?
It's a piecewise.
Yeah, it's a piecewise. Yep. Eileen, why is this a horizontal line below the x-axis? The slope is negative. Yep. Why is it horizontal? Yeah, the slope is constant. The slope doesn't change. Good. Okay. What happens over here?
Slope is constant and it's positive.
Slope is constant and it's positive. Yeah, maybe something like this. I don't know. Maybe it should have been higher, but it should be constant as well. Are we good with, actually, let's do this more. I don't have arrows here, so I guess technically my slope ends there as well. And then the slope here would end as well. All right, there we go.
So can we put that third one anywhere above the x-axis?
Now, to me, it looks like this slope is less steep than this slope. So I would prefer this to be maybe lower than this one here,
Oh,
right? Maybe here, I don't know. Maybe here. Yeah. So I think that would be the important thing that I would want to see, Kana, is that this other piece is, you're identifying that it's less steep than this slope over here. So it should be below this other piece here.